Dawn. Another day begins, powered by the sun. The energy of our nearest star is produced by nuclear fusion and provides the energy for all life on Earth. Fusion is the process of combining the nuclei of two light atoms to form a heavier one. This reaction releases energy that we can harness to generate electricity. Today, scientists from around the world are working together to better understand nuclear fusion. Scientists hope someday to replicate the sun's fusion processes here on Earth. Fusion power plants that will produce a clean, safe source of electricity with an almost unlimited fuel supply. In this video, we'll examine the great promise of fusion energy to understand what it is, why it's important, and what progress is being made in the scientific research programs around the world. To understand the difficulty involved in making electricity with fusion power, we first need to know a bit more about the structure of atoms. Atoms are the building blocks of all the solid, liquid, and gaseous matter on Earth. Shoes, shells, and surfboard wax. Anything we can think of is composed of atoms. Atoms are so small that they can't be seen. To get an idea of the size of atoms, the atoms in the eye of this mouse are about as big in comparison to the mouse as the mouse is to the whole Earth. If we visualize a single atom, we would see a cloud of negatively charged electrons. If we traveled farther into the center of the atom, we would find the tiny positively charged nucleus that holds the negative cloud of electrons to the atom. These are electrical charges, like the positive and negative poles on a battery. The nucleus of the atom has two types of particles which account for most of the atom's mass. Neutrons, which have no charge, and protons, which have a positive electrical charge. The number of protons in the nucleus is called the atomic number and determines which type of element the atom is. Hydrogen is the simplest element and has only a single proton in the nucleus, and so has an atomic number of 1. Helium has 2 protons, and so has an atomic number of 2, and so on up to more complicated atoms like iron and uranium. The arrangement of elements by their atomic numbers makes up the periodic table. In fusion research, we are mostly interested in the lightest nuclei, hydrogen and helium. Although atoms make up the solid matter around us, they're mostly empty space. If the atom with its electron cloud were the size of a classroom, the nucleus would be the size of a grain of sand at its center. Opposite electrical charges attract each other, and like charges repel one another, just like the poles of a magnet. This powerful force of attraction, called the electric force, between the negative electrons and the positive protons is what keeps the structure of atoms together. If like charges repel, why do the positively charged protons stay packed together in the atomic nucleus? If it was not for another type of attractive force called the nuclear force, the nucleus would fly apart. The nuclear force is powerful, but only over the extremely short ranges inside the atomic nucleus. If you have more than one nucleus, they're called nuclei. Fusion is the process of combining light nuclei. We've come to the skateboard park to find out how it's possible to overcome the electric repulsive force that wants to keep two positively charged nuclei apart. When they're far apart, the particles in the nucleus repel each other. But when they get close enough for the nuclear force to take over, they'll stick together or fuse into a larger nucleus. These skateboarders illustrate the idea. We can imagine that they're both positively charged like the nuclei in atoms. Here they come toward each other, but they don't have enough speed to climb the hill. The hill acts just like the electrical force of repulsion between protons to keep the skaters apart. But if they have more speed, they can climb the hill, overcome the forces keeping them apart, and if they were nuclei, fuse together. Since most scientists are not very good skateboarders, They use an energy diagram to help them visualize the fusion process. Again, the long-range electrical force creates a hill or barrier between the two nearby nuclei. The hill gets steeper and steeper as the particles get closer to one another. Without enough speed, the particles can't climb the hill and so roll back down. To overcome their mutual repulsion, the positively charged nuclei need to be moving very fast. Then, if they do manage to get close enough, the nuclear force will take over and fuse them together. This combining of nuclei is called a nuclear reaction, in contrast to the more common chemical reactions we see every day. In this fire, carbon atoms in the wood are being joined with oxygen atoms in the air to form molecules of carbon dioxide, or CO2. Any process in which atoms rearrange to form different molecules, like joining oxygen and carbon to form CO2, is called a chemical reaction. In contrast to the chemical reaction in the fire of the sun is a nuclear reaction called fusion. Any process in which atomic nuclei are rearranged to form different atoms is called a nuclear reaction. Fusion is the process of combining the nuclei of two light atoms to form a heavier one. This reaction releases energy that we can harness to generate electricity. Another type of nuclear reaction is the fission reaction. It's important to realize that the fusion reaction is the opposite of the fission reaction. Fission, which powers present-day nuclear power plants, is the process of splitting a heavy nucleus into two lighter nuclei. Many different light nuclei can fuse and release energy. The easiest fusion reaction to make work is called the DT reaction. Let's take a closer look. DT stands for deuterium and tritium, and both are isotopes of hydrogen. Isotopes are atoms that have the same number of protons in their nucleus, but a different number of neutrons. The hydrogen in water comes in three different isotopes: common hydrogen with a single proton, deuterium with a proton and a neutron, and tritium with a proton and two neutrons. When you drink a glass of water, you'd never notice the difference, but scientists have discovered that these isotopes of hydrogen work really well as fusion fuel. In fusion, as with our skateboarders, when a deuterium nucleus and a tritium nucleus get close enough together that the strong nuclear force is effective, instantly all of the nucleons, the particles that make up the nucleus of the atom, bond together to form a temporary nucleus with two protons and three neutrons. This new nucleus is very unstable, and it quickly disintegrates into two particles, a helium nucleus or alpha particle and a free neutron. We started with hydrogen and ended up with helium. That's the same gas that they use in blimps and party balloons to make them lighter than air. But there's a bit of a mystery, because when the reaction is done, something is missing. If we weigh the deuterium and tritium nuclei before their fusion, and the helium and neutron that are left after the fusion, we find that despite the fact that the total number of neutrons and protons has remained the same, some of the original mass has been lost. This missing mass has been converted into energy, the kinetic energy of motion of the neutron and the helium. Using Einstein's famous formula, E equals mc squared, we can calculate how much energy was released in this one fusion reaction. Each individual fusion reaction, like the one we just looked at, releases about 1,000,000 times more energy than the energy released in each individual chemical reaction in an ordinary wood fire. And unlike wood, oil, or other chemical fuels, there's an almost limitless supply of fusion fuel available to every person, culture, or nation on Earth in the seawater that makes up the oceans. The chemical formula for the water molecule is H2O. That means that for every water molecule, there are 2 hydrogen atoms. About 1 in every 6,000 hydrogen nuclei has the extra neutron to make it deuterium. So, even though the energy released in each fusion reaction is tiny, there are so many deuterium nuclei in normal water that if we took all the deuterium from the top 1 inch of San Diego Bay and used it for fusion fuel, we could provide enough energy to run the city of San Diego for 50 years. The deuterium in the top 1 inch of the world's oceans could supply the energy requirements of our planet for 100,000 years at the present rate of consumption. Since we would only need 1 out of every 6,000 hydrogen atoms, we'll never notice a change in the oceans. The tritium necessary for the DT reaction is easily obtained from a nuclear reaction with the element lithium. So you can see, success at developing fusion power would be very important for the world. With such an abundant supply of fusion fuel and so many people trying to make fusion energy happen, why don't we have fusion power plants on Earth to generate our electricity already? Well, there are a number of technical obstacles that make fusion difficult. If we remember the skateboarders, they needed enough speed to be able to climb the hill and join together. With nuclear particles, increasing their average speed so that fusion can occur means increasing their temperature, since hot particles are moving faster than cold ones. For one common fusion reaction, we know that the temperature required for fusion is about 100 million degrees Celsius, which is even hotter than the center of the sun. At such high temperatures, the atoms are moving so fast and colliding with such force that molecules are broken apart and even the electrons are stripped away from their nuclei. This means that the nuclei, or ions, and the electrons in the deuterium-tritium fuel mixture of a fusion power plant are flying around, crashing into each other without any of the normal, orderly atomic structure at all. A mixture like this is called a plasma, the 4th state of matter, along with gases, liquids, and solids. By the way, the plasma of physics is not connected in any way with the more familiar blood plasma used in hospitals. They just happen to have the same name. Actually, we see plasmas all the time. The fluorescent lights you're probably sitting under right now contain minute quantities of plasma. Plasma also occurs in neon signs, arc welding, and in nature, in lightning. Fusion fuel, in the form of a plasma, has a lot of interesting properties that allow us to use it, study it, and hold it inside fusion reactors. Let's take a look at how we catch lightning in a bottle. If we tried to confine our fusion fuel in a cylinder made from any solid material, 2 things would happen. First, the high-temperature fuel will come into contact with the wall of the container and transfer some of its heat energy to the wall. Second, the hot fuel would cool down to below fusion temperatures so that the fusion reaction stop occurring. In order to make fusion work at all, we have to make sure that the fuel stays hot, and this means that the fuel can't be allowed to touch anything. How can you hold something without touching it? In the case of plasma, with a magnetic field.
We're going to use this machine to show how magnetic fields can be used to influence a plasma. I've made a weak plasma in here by just applying a high voltage across a gas that I've pumped out. And now that I'm applying this horseshoe magnet, you can see that it can move the plasma around pretty strongly. But a horseshoe magnet can't be turned on and off, and they're very big and heavy. So instead, we like to use electromagnets to control our plasmas. And now, if you'll watch, the electromagnet squeezes the plasma away from the walls of the tube, so it's hotter and brighter than it is when the electromagnet's off. So we use electromagnets like this in order to do our fusion research.
Any charged particle, like the protons, electrons, and nuclei that we've been talking about, which is moving across a magnetic field, will experience a force, This force will be perpendicular to the magnetic field and the direction of motion of the particle. This effect is used in lots of practical ways, such as to steer the electron beam that paints the picture in a television tube. In fusion research, we use magnetic fields to confine the electrons and ions of the fusion plasma. Here's how it works. If we create a magnetic field inside of a cylinder, the ions that were going to hit the wall are deflected into a circular path around the magnetic field and away from the walls of the cylinder. Increasing the strength of the magnetic field decreases the radius of the circular path the ions follow and holds them more tightly in the magnetic field. This seems like a good way to confine our fusion plasma, except that the plasma can escape from the ends of the cylinder. The easiest way to close off the ends of a cylinder is to bend it around and put the ends together, creating the shape of a torus. That's not a car, by the way. It's a shape like a donut. Charged particles, either protons or electrons, that are traveling toward the walls of the torus are deflected away, while particles traveling around the torus are gently guided by the field around and around. This way, the hot plasma particles are kept from touching the walls, and their temperatures are kept high enough that fusion reactions begin to occur. The magnetic field forms a magnetic bottle that confines the plasma inside the torus. In fusion research, the container we keep the plasma in is called a vacuum vessel because it contains a vacuum, like a light bulb, where the plasma is created. The powerful magnetic field is created by coils that surround the vacuum vessel. This type of fusion confinement device is called a tokamak, a word coined by Russian researchers who did a lot of early work on fusion. What you see here is the D3D tokamak, which is located in San Diego, California. It may not look like a donut because of all the extra equipment used in fusion research, but buried in the middle of all this is a torus containing a fusion plasma. So how are we doing in our attempts to perfect fusion power? This graph shows how much power has been produced in various experiments around the world. The basic message is that each year has brought improved performance from these machines. Most recently, the TFTR tokamak at Princeton University in New Jersey produced 10 megawatts of power. If this power was completely converted into electricity, it would be enough to briefly light 100,000 household light bulbs. We know how to confine the plasma, and we know how to heat it to fusion temperatures. Now we're designing a large experimental tokamak, which when operating should produce as much power as a standard power generating station, about 1,000 megawatts. If this power was completely converted into electricity, it would be enough to briefly run 100,000 homes. The name of this next experimental machine will be the International Thermonuclear Experimental Reactor, or ITER for short. The development of fusion power from scratch has been a massive technological challenge, comparable to the production of the 747 jumbo jet, finding a cure for cancer, or landing a man on the moon. An entirely new science had to be developed, along with the technology and the theoretical understanding of plasma physics. This work had to be done with no model or prior picture of what a fusion reactor should even look like. For the scientists and engineers that have devoted their lives to fusion research, the challenge and progress have been rewarding. We're getting close to fulfilling the promise of safe, non-polluting, abundant energy in our lifetimes. So as you can see, the future looks brighter than ever.